Hello, I'm Vincent Rooyakkers, and this is Lab 1 Tape. In this lab, we examined the electron donating/taking properties of tape. There were two main goals in this lab, the first being to determine an unknown charge based on the gravitational force in the system and the distance moved by the system. In the case of this lab, there was no distance moved, and so we can deduce from this that the net force was equal to 0, and therefore the electric force must equal the gravitational force. Another goal is to be able to tell whether an object has a positive or negative charge. In the case of the lab, we did a simple test where we rubbed a plastic pen in our hair, and since the tape was attracted to this negatively charged pen, it indicates that the tape must have a positive charge. There were three main principles used in this lab, the first being Coulomb's law, which we simplified it down to the charge of the system times the electrical field acting on the system. In this case, this would give us the electrical force, and this we know is equal to the gravitational force. We also used the principles of electrical fields throughout this lab. Of course, in the case of the lab, it helped us to determine what direction the force should be. Since we know the tape has a positive charge, we know the field is going away from it in case of the system. So in the case of the system here, since it's a positive charge too, it would not impact the direction of the field that it has on the force, and the force would just continue to go in the same direction of the field, which is up, which opposes gravity. And again, we use Newton's second law here, which is the sum of all forces. Since the object's not moving, it has no acceleration, so therefore the net force has to be equal to 0. And this is how we can determine that the electrical force will equal the gravitational force. Let's look at my computer model. So now that I've determined that the amount of electrons lost by the tape and the charge of the tape, I need to determine if this was a reasonable approximation. So I constructed a computer model that iterates the integer amount of electrons until we find a point where the electrical force is approximately equal to the gravitational force. The calculation is mainly the same that we've seen with Coulomb's law in combination with Newton's second law. There's nothing new there. If you know how to program those, you know how to program it here. But in the case of my lab, we run into some memory constraints if you just continuously add 1 over and over again. So I constructed a while loop that iterates large numbers of electrons since this integer amount. So what it basically checks is how close the electrical force is equal to the gravitational force. And if it's not that close, it adds a large number of electrons, and as it gets closer and closer, it adds less and less electrons, but there's still large amounts. So what this basically did was cut down the amount of iterations needed from like millions and millions, because if you actually look at the amount of electrons, I think it's like in the billions or something. And I managed to reduce the amount of iterations down to 400 iterations through this while loop. And based off of that, I could get it down to what my answer was with 6 significant figures, which is why I use 6 significant figures here. Hypothetically, since like my measurement actually wasn't even that exact to begin with, because I was using a ruler I bought at the French Walmart, so that was only like 1 sig fig of accuracy anyways. But hypothetically, if I had more precise measurements, this would indicate I could get it. This while loop could get it down to 6 significant figures of accuracy. So now let's watch it run. Here we see the gravitational force being the yellow arrow, with the electrical force being the orange arrows. These are approximately equal in size. So again, just demonstrating that the net force is equal to 0 and the object, why the object remains stationary. And we see, oh, actually, what was the magnitude of the charge? Just to reiterate it, here it is again. There was only primarily one assumption in this, and that was that each tape acted as a point charge. For the question, what if the electrons had a positive charge and the protons had a negative charge? Since the tape was losing electrons, this means the tape would be a negative charge overall. And a negative charge leads to a negative field. For instance, in the system, the one tape would have a negative field which points in towards itself, and the system itself had a negative charge. So this would be multiply direction by -1, which would go up. So again, this would just be the same result that we had before, no impact. So for why is it important to handle the charge tape as little as possible? When the tape comes into contact, it repeats the same process where it gained its charge, and it would either lose electrons to my hand or pull some electrons off my hand. And that's why it's important to not touch the tape unless it's on the ends.